me start recording this video. Okay, so it's getting recorded. Okay, so I guess my screen is visible. Okay, recording. Yeah. Okay, so good evening all. So we'll have our online session on the course Analog Circuits, NPTEL course Analog Circuits, and today we will be dealing with the week 5 portions. So the problems related to week 5 portions. The course instructor for this course is Professor Jayanta Mukherjee from IIT Bombay, and I am Narayanan PP, teaching assistant for this course. I'm a research scholar from IIT Palakkad. So let me start. So already we are 2 minutes late, so we'll start the session directly. Let me start with the first question. So I guess I'm audible, right? If I'm not audible, please let me know. Okay, so let us start with the first question. So first question is, so basically this week sir covered mostly the portions related to the gain margin, phase margin, and that is related to the stability of the system, and some frequency compensation, also design of Butterworth filter. Right, so we'll be dealing with the same question. So I think almost the same, a few of the gain margin, phase margin related questions was covered in the previous class also, right, in the previous tutor also. So we'll be initially dealing with a similar type of similar type of questions. So this is one question. So let us start with the first question. So the first question is, the transfer function of a system is given as g of s equal to 50 by s into s square plus 10s plus 5. The system is placed in a unity gain negative feedback. So the feedback is unity, is having a gain of 1, right? So determine the phase crossover frequency. So it's a direct question. So what is so let us draw the system first. So we have a feedback system, that is negative feedback system. Okay, so let it be h of s be the feedback. Okay, so this is v in and this is v out. Okay, so since it is a unity feedback system, what is h of s? H of s will be equal to 1. So we can draw this system as g of s. So somewhere here. Okay, so this is actually the system. Okay, so the question is to find the phase crossover frequency. So we know, like for what is phase crossover frequency? It is a frequency, like we have the loop gain. Sorry. Let me write this. Okay, so we have the loop gain g of s into h of s. So the angle of g of s into h of s. Okay, angle of g of s into h of s. So at what frequency this angle, say it starts with some value, at what frequency it crosses the minus 180 degree, right? So that is the actually the phase crossover frequency. We will denote as omega PCF. Okay, so this is actually the phase crossover frequency. So how to find this? It's pretty much straightforward. We just need to equate the angle of this transfer function, that is g of s into h of s. Okay, so this g of s into h of s to 180, and we'll just find for what value of omega the angle is equal to minus 180, right? So we'll do that. So let me correct this. So what is g of j omega here? G of j omega into h of j omega. Okay, g of j omega into h of j omega is equal to g of h of j omega is 1, right? So we can write it as t by j omega into, so this is s square plus 10s plus 25, right? So it is s plus 5 whole square, right? So this is equal to s plus 5 into s plus 5. Okay, so that is the denominator. So we can write here as j omega plus 5 square. Okay, so here 50 by j omega into j omega plus 5 into j omega plus 5. So what is the angle of g of j omega into h of j omega is equal to, so I think there is no values in the numerator, so we can write as minus tan inverse. Okay, tan inverse. So first term is omega, j omega. So the angle is real imaginary term by real term, right? So omega by 0 minus tan inverse of, here it is omega by 5, and for third term it is again minus tan inverse of omega by 5. So this term is 90 degree, so minus 90 degree minus 2 tan inverse omega by 5. So this is the angle. Okay, so this is the angle. We can represent that as theta. The question is to find crossover frequency, phase crossover frequency. So we just need to equate this theta at phase crossover frequency. Theta is equal to minus 180. So we'll just equate this. So minus 90 degree minus 2 tan inverse omega by 5 equal to minus 180. So that is tan inverse omega by 5. So this cancel off, so it will be 90, right? Minus 90. So if I just rearrange, so by 2 means 45, so this will be equal to 45 degree. So omega by 5 equal to tan 45, this will be equal to 1. So what is the frequency? Omega equal to 5 radians per second. So this is the gain crossover, sorry, phase crossover frequency. Okay, so this is the solution. I guess it's clear. Like let me again brief it. Like we just need to find the phase crossover frequency. So in order to find the phase crossover frequency, we just need to find the angle, sorry, the frequency at which the angle crosses minus 180 degrees. So what we will do is, like, we'll just initially we'll write what is the angle based on this g of s into h of s. So we have written this angle, and this is the angle theta, and we'll just equate this to minus 180, and just a few computation will get what is the value of omega. So the phase crossover frequency that we got is 5 radians per second. Okay, so let me show the solution that I've written. So this is the solution, the same thing, whatever I have mentioned or elaborated now, the same thing I have written here. So that is the first question. So let us come to the second question. So the same question is being repeated, we just need to find the gain margin. So what is gain margin? So gain margin is the gain at phase crossover frequency, right? So what is the, so for example, see how we can draw this body plot. So initially at s equal to 0, infinity, right? So it start from infinity. It has a roll off of minus 20 dB, right, initially, and at a particular frequency, that frequency is 5. At 5, its roll off is minus 60. Okay, we just need to find so this is okay. So what is the phase? Phase will be somewhat like this. Okay, so at particular frequency we got it to be minus 180 degrees. So we just need to find what is the gain. What is the gain at that frequency, omega GC, omega phase crossover frequency. So whatever is the gain at that crossover frequency, that is the gain margin, right? So that's what we are going to do. So we just need to, already we have found what is the phase crossover frequency. We'll just substitute that here. So before that, what is the gain here? Gain from G of S. So G of S, we have already written it as like 50 by S into S plus 5 into S plus 5. Okay, so what is G of J omega gain? So this is actually G of S into 1. Okay, so that is actually the loop gain. So I'll write as L of S, G of S into 1. So let me write this as L of J omega, loop gain. Okay, so that equal to, so what is a gain? So let me take it as mode. Okay, and also I'll take it in dB. So it will be 20 log, right? dB means 20 log. Okay, so how we'll take the gain here? We just need to, so S means omega, right? Omega into, so this is actually S plus 5 whole square, right? S plus 5 whole square, that equal to J omega plus 5 whole square. Okay, so what is the mode value? Okay, what is amplitude value here? That is like A plus J omega, JB means A root of A square plus B square, right? So root of 5 square plus omega square. So that is the amplitude value, that whole square. So this will be equal to 5 square plus omega square. Okay, so that we will substitute here. So what we will get is like 5 square plus omega square. So this is the loop gain. So here we need to find the gain margin, right? So gain margin is equal to, is what is the loop gain at the phase crossover frequency. So we'll just substitute the value that we have we got in the previous question. So I guess that omega PCF was 5, right? So we'll substitute that 5 square plus omega is omega PCF, so 5 square. Okay, so log to the base 10, so we'll get some value in dB. So that is a gain margin. Okay, so let us check. So let me rub this. Okay, so I've done the same thing. So we'll get the gain margin to be minus 13.979 dB. So this is the gain margin. So let me again brief it. We already got what is phase crossover frequency. To find the gain margin, we'll just substitute the gain value, loop gain at omega equal to omega PCF, and just substitute that, and we'll get whatever in dB, that is the gain margin. Okay, so that is about the second question. So it's pretty much straightforward. Let me go to the third question. Third question is the same question. The transfer function of a system is given as G of S equal to the same gain gain. So open loop gain. The system is placed in a unity gain feedback, negative feedback. Determining the gain crossover frequency. The question is to find the gain crossover frequency. So again, what is gain crossover frequency? So here G of S, or let me write as loop gain, L of S. Okay, so how L of S varies? So initially it starts from 0 as at infinity, at a minus 20 dB it will have a roll off until last till omega equal to 5, and after that it will go with minus 60 dB, right? So at a particular point, or at a particular frequency omega, it crosses 0 in dB or crosses 1 in gain. So what is the gain crossover frequency? It is a frequency at which the gain of loop gain, okay, loop or the amplitude value of the loop gain is equal to 1. Okay, so we just need to find what is the frequency. So what we'll do, we'll just substitute the gain or loop gain equal to 1, and we'll find what is the frequency there. Okay, so we know, so here loop gain L of S is given as g of s into 1, so that equal to, so already we have got t by s into s plus 5 whole square. So in j omega, L of j omega is equal to 50 by j omega into j omega plus 50 whole square. So what is the amplitude? This one, mode of this value. So what we will do is, to find gain crossover frequency, we'll substitute, or we equate this to 1. Okay, so on equating this to 1, so what is this? 50 by, the mode value is omega into, this is root of omega square plus 50 square, right? So omega square plus 50 square, that whole square, so it will be equal to omega square into 50 square, right? So that equal to 1. So 50 equal to, so if I multiply this as omega into omega square plus 50 square, just expand omega cube plus 50 square
Sir,
omega. Yeah. Oh, this is not
sir,
50, this is 5. Sorry, this is 5. Okay, let me rub that. Okay, so this is 5. Okay, so sorry for that. So that is 5 square. Okay, so we can write as omega square plus 5 square omega minus 50 equal to 0. So we just need to solve this equation. We will get 3 values. Take the positive value. Okay, so that is the gain crossover frequency. So we'll get some, so 1.7 something. Okay, so let me check what is the value. So you'll get 1.776 radians per second. So that is the gain crossover frequency. So let me brief it again. So in order to find the gain crossover frequency, we just need to equate the gain to 1, loop gain to 1, and find what is the frequency. So that's what we have done here. The same step. So t by omega into omega square plus 5 square equal to 1. So we'll get this equation, solve this, we'll get omega. So this omega, okay, omega equal to 1.776. So that much radians per second, that is a gain crossover frequency. Okay, so only the remaining thing. So we have found the phase crossover frequency, corresponding gain margin. We have found gain crossover frequency. Now the only remaining thing is phase margin. So the next question is related to the phase margin. Okay, so we just need to find phase margin. So how to find the phase margin? We already know, like if say this is the response, and at particular point the gain crosses 0 in dB or 1 in gain. So this is the gain crossover frequency. And what is the phase change, or the phase, or the angle, margin of this angle from minus 180 degree? Okay, what is the margin of this angle? So this is the angle at omega GCF. So what is the margin of this angle from minus 180 degree? So that is the phase margin, right? So that's what we need to find. So that is the next question. Okay, so that is the next question, determine the phase margin. So what we'll need to do, just we know what is the equation for theta, right? So we just need to find what is theta and what is phase margin. Phase margin is equal to this theta minus 180. So this is the phase margin. So we just need to find theta. So how to find theta? Theta equal to, we already calculated the value of angle, right? So minus 90 minus 2 into tan inverse, it is omega by 5, right? This is the angle. Okay, this is the angle. So what is phase margin? Phase margin equal to this theta at omega equal to omega GCF. Okay, so minus 90 minus tan inverse omega GCF by 5 minus of minus 180. So we'll write as plus 180. So we got omega GCF equal to 1.779 in previous question. We just need to substitute this here and you'll get phase margin. Okay, So we'll just see what was the phase margin available, means calculated. So let me clear this. Okay, so on substituting omega GCF as 1.776, I got means on substituting this we'll get the phase margin as 50.889. So it's near to 51 degree, or 50.889 degree is a phase margin. So this is all about the 1 to 4 question. So it is all related. Just we have been given a system. We know it's open loop gain and closed loop gain. A question is to find all the parameters, that is gain crossover frequency, phase crossover frequency, gain margin, and phase margin. Okay, so that is very simple. We'll go to the next question. Okay, so the question 5th is again related to question 4th. So in question 4th, if the phase margin is changed to 40 degree, okay, the phase margin is changed. So we got in the previous question as phase margin as 50.889. So the question is like we have changed the phase margin, or we need to change the phase margin to 40 degree. So what will be the new gain crossover frequency? Okay, so we know phase margin equal to, so what from the previous question, definitely the theta will be minus 90 minus 2 tan inverse omega by 5, right? Omega by 5 minus or plus 180. Okay, so that was the phase margin. So the question is to find the gain crossover frequency if this phase margin is changed to 40. So what we'll do, just find what is omega, that's it. That is the gain crossover frequency, right? So what will be minus 2 tan inverse omega by 5. So minus 90 plus 180. So this will be 90, and this will be 40 minus 90, right? So minus 50. So find, so you can directly find tan inverse omega by 5. Okay, so 25. So omega equal to 5 into tan 25. So this is the new gain crossover frequency. Okay, so let me check what is the value. So the same thing, I have substituted the phase margin to 40, and we found what is omega GCF. So we got omega GCF as 2.3315. So initially it was 1.776, right, radians per second. So if I change this phase margin to 40, so the new omega GCF will be 2.3315. So the frequency has shifted. Okay, so that is a question. So but how this phase margin would have changed? There is some changes, right? So there is some change in the feedback factor. So that is the next question. So question is like in question 5, for this new gain crossover frequency, what should be the gain for the negative feedback system? So definitely there will be a change, right? G of s has not been changed. The only change is like the phase margin has to be changed. So what will the what should be changed then? So that will be the loop gain, that is only having the effect, right? Rest all is constant. So we have changed h of s. So we just need to find what is h of s. So here how we will find that? So we know at gain crossover frequency, okay, at gain crossover frequency, mode of g of s into h of s is equal to 1, right? So we know what is g of s. We just need to find what is h of s. So h of s equal to 1 by g of s. Okay, so what is g of s? That is 50 by s into s plus 5 whole square. And what is g of j omega? Equal to 50 by omega into omega square plus 5 square. Okay, we substitute the value of omega GCF here. So at omega GCF, g of j omega into h of j omega is equal to 1, right? So h of j omega equal to 1 by g of j omega. Okay, so just substitute omega GCF here, you will get a value, say some constant k. You substitute here, so you will get 1 by k, that is the h of j omega. So that is the new feedback gain. Okay, so how we shifted, initially it was at at gain cross of frequency, it was near to 50, right, 50 degree. So it has been changed to some 40 degrees. So how it has been changed? It has been changed by changing the value of loop gain. So how we will find the loop gain? We substitute, or we find initially what is the omega GCF based on the change in the and the angle, and we'll substitute that here, and we can find what is h of j omega. So we'll see what is the value. So at gain cross of frequency, the what is g of j g of s into h of s, that is equal to 1. We substituted that, and on substituting, we'll get h of s equal to 1.419. Same step. So this is the change in the feedback. So initially it was we took it as a unity feedback gain, right? So but here we have found that h of s equal to 1.419. So this is the feedback gain. So I guess it is clear. Okay, so let us go to the next question. So before that, let me check whether it is, yeah, okay. Okay, so that's all about the sixth question. So coming to the seventh question. Seventh question is, consider an inverting amplifier such that the open loop gain of the amplifier is given as g of s equal to 10 power 7 by s plus 100 into s plus 1000. So this is the open loop gain of the inverting amplifier. So this is the inverting amplifier given. If R1 equal to 10k and R2 equal to 100k, then draw the Bode plot. So the question is like they have given. So here though it is, so it is not a, so this is actually g. Okay, g of s. Okay, so they have given what is g of s, and also given what is the value of R1 and R2. The question is to find the draw the Bode gain plot of loop gain. Okay, so it went below this image, so I'll correct it. Okay, so we just need to find what is the Bode plot of the loop gain. Okay, so how we'll find? So here what is g of s? G of s being given here, so g of s equal to 10 power 7 by s plus 100 into s plus 1000. Okay, so we can draw the gain plot here. Okay, so there are two cutoff rate at 100 and 1000. So let it be this be 100 and this be 1000. This omega. Okay, so initially at very low frequency 0, the value will be at a constant value, right? So we just need to substitute the omega value, j omega value, and you will get a constant value, say some k. Okay, at 100 frequency 100, there will be a change in the amplitude. So it will roll off, it will have a roll off at -20, right, -20 dB. Okay, so this is all about g of j omega. Okay, and after 1000 the next value will come, right? So at 1000 it will come like this, so -60 dB. Okay, not -60, -40, sorry, -40 dB. So this is all about g of j omega. Sorry. Okay, now we'll check what is the feedback gain. So what is the feedback here? So here V0 is the output. Okay, and this is the input. So they have not mentioned that this is non-ideal, so we'll consider it to be ideal. So and not given anything any relation related to the input resistance, so we'll consider this Rin as infinity. So what is the feedback here? Feedback due to output V0 So feedback will be, say, we'll consider it as VF. So feedback due to output is V naught into R1 by R1 plus R2. So what is the feedback gain here? Beta equal to R1 by R1 plus R2. Okay, so 100, sorry, R1 is 10K by 10K plus 100. So 10 by 110. So this is the beta value. Okay, so if I draw the okay, so if I draw the amplitude or the Bode gain plot of beta. Okay, let it be in dB. Okay, so this is k dB. So I'll take in dB. Okay, so what is in dB means 20 log of 10 by 100. So it will be some 110. So it will be some negative value. So it will be somewhere here. So I'll represent it as minus k1. Okay, so minus k1. Okay, now we need to find actually we need to find the Bode plot of loop gain, right? So what is loop gain? Loop gain is h of s or g of s into beta. G of s into beta. So in dB we can write as 20 log g of j omega into beta. Okay, so this is actually the gain. So I can split this, right? It is like 20 log g of j omega plus 20 log beta. Okay, so we just need to add these two gains. Sorry, these two gain in dB, right? We just need to add these two gain in dB. You will get the entire loop gain. So we have plotted g of j omega, right? G of j omega in dB. That is 20 log of g of j omega. I have also plotted beta in dB. Okay, that is what these two values represent. These two values, 1 and 2. So what is new loop gain? L of, say, L of s or L of j omega. We just need to add g of j omega in dB. So I represent dB in dB plus the loop gain. So not loop gain, the feedback gain. So let us represent as beta as in dB. So I just need to add both these. So what I'll get if I draw here, it will be like summation of this and this. So if it is negative, since it is minus k1, whatever is the value here, that minus k1 will be initial value. So it will start at some value k minus k1 dB. Okay, and we just need to subtract. So I'll get somewhat like this graph. So the thing is, like, I have subtracted g of j omega in dB minus beta. So that is some k1 dB that I subtracted. So this is the Bode plot of the loop gain. Okay, so this is what we have plotted. So let me show that. Okay, so here as I mentioned, from the circuit h of s, that is beta that we mentioned, is r1 by r1 plus r2. So I got some value. So in dB it is minus 20.828 dB. Okay, on substituting this. Okay, so I draw the Bode plot of g of j omega. So I'll get some 140 dB. I guess it is not 140. G of j omega will be equal to, at 0 will be 10 power 7 by 1000 in 100 into 1000, right? So maybe 10 power 7 by 10 power 5. So it is actually 10 power 2. So in dB this will be 2 into 20, so 40 dB. Okay, sorry, so it is not 140, it is actually 40 dB. Okay, so I'll correct it here itself. So it is actually 40. Oh, I can't correct it. So I'll correct it and post.
Excuse me, sir.
Sure, yeah. Hello.
Polarity or reverse are given sir,
What?
in the positive
Oh,
terminal
yeah, yeah,
feedback.
correct. That was by mistake actually. This is minus. Okay, this minus and this plus. I give it as this minus. This is actually inverting. Yeah, inverting amplifier. I'm really sorry for that. Okay, I'll correct it while uploading in the drive. I also correct this also. This is actually 40. Okay, and I think okay. So this is g of j omega in dB, and this is h of j omega in dB. I got as minus 20.82. So what is the net value? I just need to add this and this. So this value is wrong. So 40 minus 20.82. So that will be the value. Okay, some 19 point something. That will be the value here. So the entire the body gain plot of g of j omega in dB will be shifted downward. That is what we can see there. Okay, that is the what we can see here. Okay, so definitely there will be change in gain crossover frequency and all when such a feedback is connected. So that is what we have to take away from here. Okay, so I guess it's clear. So I'm sorry, this will be negative. Okay, I will correct it while uploading in the drive. Okay. Okay, so coming to the next question, consider an inverting amplifier. So same question, I guess. So consider an inverting amplifier such that the open loop gain of the amplifier is this. So same question. If a resistance R is connected such that the phase margin of the inverting amplifier is set to 60° as shown in figure. So we don't know what is the phase margin of the previous circuit. Okay, so we have not calculated, but the question is like they have connected a new resistance here, a new resistance R here. So again this is minus. Okay, this minus, this plus. So it is connected at inverting terminal, a resistance R. So the question is to find the value of R such that the phase margin of the entire amplifier is shifted to 60. Okay, so that is the question. So question is like in order to change the phase margin, they have connected some resistance R. And what was the value of R then? What was the value of R such that the phase margin of this amplifier or this feedback configuration goes to 60? Okay, so given R1 equal to 10, R2 equal to 100 and all. So we'll find that. Okay, so how we'll find that? So initially we'll find what is a frequency at which this 60° happens, right? Phase margin, we know phase margin equal to the angle theta at gain crossover frequency, right? GCF equal to minus 180. So this is the phase margin. Okay, so before that, what is the angle theta GCF? That we'll find. So here from the question, G of S, right? G of S equal to 10 power 7 by S plus 100 into S plus 1000. Okay, this G of S. And what is H of S here? H of S equal to, so here what happened is like there is one more resistance R here, right? There is one more resistance R here. So what is the feedback at this point? At this point due to V naught. So V naught into the effective resistance at this point, right? What is the effective resistance? So I will draw here the network. So we can consider V to be 0 to find the feedback. So we will supply some V naught here. So R1 here and R here and R2 here. So this is the feedback voltage. So what is the feedback voltage here? If Vf equal to V naught into R1 parallel R, right, by R1 parallel R plus R plus R2. Okay, so this parallel configuration in series with R2. So that's why R1 parallel R by R1 parallel R plus R2. Okay, so voltage distribution. So H of S equal to R1 R2. So I will call it as some beta. Okay, so what is the gain? Loop gain here, G of S into H of S equal to some 10 power 7 by S plus 100 This plus 1000 into some beta. So we can see here all values, all the components connected here is resistance, so it is frequency independent. So angle of g of j omega h of j omega, that is theta, right? Theta is given as, I'll write here, so at minus tan inverse of imaginary term by real term, so omega by 100 minus tan inverse of omega by 1000. So I'll get some value. Okay, so some value here. So we don't know what is omega, right? We don't know what is omega, so this is the angle here, theta. This is the angle here. So the question is like, they have given at we need to find what was the IR value. So before that, we know, since question has been given as phase margin, right? Phase margin to be 60 degree. So what is phase margin here? Theta plus 180 equal to 60. So theta we know here as minus tan inverse omega by 100 minus tan inverse omega by 1000 and plus 180 equal to 60. So solving this, I think we'll get omega, right? So how we'll solve this? This minus tan inverse a minus tan inverse. So we have seen last week, tan inverse a plus tan inverse b is given as tan inverse a plus b. So this is a property. So by 1 minus ab. Okay, we'll use the same equation. So I'll get some value as tan inverse in terms of omega. Okay, you substitute this value as a and b, you'll get a value that equal to 120, right? So solving this we'll get an omega, that omega is omega GCF, gain crossover frequency. Okay, so that is omega GCF. So we'll see what is the value of omega GCF that I got. Okay, so I substitute the same value. So see, we have substituted tan inverse of a plus tan inverse of b. So on substituting this, we got omega GCF as 317.54 radians per second. So this is a omega GCF. So but our ultimate aim is to find R, right? So how to find R? So we know at omega GCF. So what is the peculiarity of omega GCF? It is a gain crossover frequency. So at gain crossover frequency, g of j omega into h of j omega is equal to 1. So we know g of j omega, so that is 10 power 7 by j omega plus 100 into j omega plus 1000. So this is g of j omega, that into h of j omega is r1 parallel r by r1 parallel r plus r2, that equal to 1. Okay, so here this I'll write it as for mode value. So it will be omega square plus 100 square, root of omega square plus 100 square into root of omega square plus 1000 square, that into, how we'll write this, r1 parallel, so r1 into r, right, by, so if I solve this, it will be somewhat like this. So r1 into r plus r2 into r1 plus r equal to 1. So we can substitute here omega equal to omega GCF value. So what value got? I think some 300 something value. So I'll just substitute this omega GCF. I'll get a value here k. I know what is the value of r1. I know what is the value of r2. We just need to find what is the value of r. So just that is a simple computation. You just substitute these values, cross multiply, you can find what is the value of r. So that is the value of r at which we can have the phase margin at 60 degree. Okay, so we'll see that solution. So already we got omega GCF. Okay, I substituted that value. So this mode of j omega into h of j omega equal to 1. So substituted the value of omega here Okay, and I also substituted what is the value of R1 and R2, and on just cross multiplying and simple computation, I will get R, the value of R as 5.672 kilo. Okay, so this is how we will find the value of R. So the question, the main takeaway is like we have an inverting amplifier, and say it due to some reason the again we have very low phase margin. So in order to increase the phase margin, so some value above 45 and all, then we may just add a resistance here and find the value of resistance that has to be added. So we may be knowing what is G of S. So here it is minus. What is the value of G of S here? You calculate what is the value of R in the same manner here, and substitute that and just connect that R here. So that system will be more stable than the previous one. So so that is a takeaway. Okay, so I guess it's clear. Okay, so now let us go to the ninth question. The question is based on Butterworth filter design. So the question is, you are designing a Butterworth filter with these specifications. So omega p equal to 10, omega p equal to 10k radians per second, omega is equal to 100k radians per second, A max equal to 3 dB, A minimum equal to 60 dB, and DC gain to be 10 dB. Determine the value of epsilon. So for designing a Butterworth filter, we should know the general transfer function of Butterworth filter, and how and what is this omega p and omega s, and also generally the general transfer function T of s is given as some k. K is the DC gain equal by root of, so it is in j omega, T of j omega. Okay, so 1 plus some epsilon into omega. Okay, omega by omega p power 2n. So this is the general transfer function of a Butterworth filter, and what this omega p and omega s denote, we'll see. So this is a general so this is actually the frequency response of a Butterworth filter. Okay, so at 0 frequency, this is the DC gain, so that is k, and here we say 2 frequency. One is this cutoff frequency or the end of the pass band, so that is given as omega p, and we'll we'll mention as omega s as this start of the stop band. Okay, so this is omega p and this omega s, and what is omega p? Omega at omega p, what is A max? A max is the maximum gain change from DC gain. Okay, maximum gain change from DC at omega p, so that is A max. And what is omega, sorry, A minimum? A minimum is the change, the minimum, okay, minimum gain change in the gain from DC at omega s, so that is A minimum. So these are the values that I begin. What is the end of the pass band omega p, start of stop band omega s, and what is A max and what is A minimum. Okay, these values has been given here. We need to find even the DC gain has been given. We need to find what is the value of epsilon. Okay, so how we'll find? So initially we know, right? So this is all in dB. Okay, all in dB. So 20 log of T of j omega will be equal to 20 log k by 1 plus epsilon omega by omega p power, sorry for the for my handwriting. So okay, so this is in dB. Okay, so at omega equal to omega p, so what happens at omega p? So we know at omega p, what is the value, what is the value here? So let me change the color. So what is the value here? That is T of, this is actually the T of j omega p, right? So what is T of j omega p here? It is at DC is 20 log k, sorry, 20 log k, 20 log k is the DC gain, so in dB. So 20 log k minus this amax value, so that is the gain in dB of the Butterworth filter. Okay, so you can substitute here at omega p. The value of gain will be 20 log k minus amax, that is amax here is 3 dB, right? So 3 equal to 20 log, so I can split this, right? So log a by b is log a minus log b, so 20 log k minus 20 log root of 1 plus epsilon omega by omega p. So omega we substitute as omega p, so omega p power 2 power n. Okay, so this 20 log gone, this is minus minus 1, so we can write it as 3 equal to, this is 20, so I can bring this root, right? So 20 by 2 log of 1 plus epsilon into omega p by omega p is 1 power 2n is 1, so 1 plus epsilon. So here the only value that we need to term is of epsilon, so we a simple computation we can find that, right? So this is 10, so log of 1 plus epsilon equal to 3 by 10. What is 1 plus epsilon here? 10 power 3 by 10. Okay, so epsilon equal to 10 power 3 by 10 minus 1. So this is the epsilon value. Okay, so that's how we'll find epsilon value. So that's what I have written here. So this is the solution. We know the general transfer function. In generally, the Butterworth transfer function is given as T of j omega equal to this value. We'll substitute the value of omega as omega p, and we know a max equal to 3 dB. So at omega p, the change is a max. So what is the net gain? That is 20 log k by minus 3 dB, right? So we'll equate that. So on equating, we'll get a relation. We just need to rearrange and calculate. So we'll get epsilon as equal to 0.997. So this is the epsilon value. Okay, so this is the epsilon value. This is how we'll find the epsilon value. Now coming to last question, the same question. See, the same question. You are designing a Butterworth filter with the following specification. The question is to determine the order of filter. So we have found how to find the epsilon value. Now how to find what is the n value. So already we know epsilon. The remaining, so if I substitute here omega equal to omega p, this term will cancel, right? This will be equal to 1 power 2n. So the effect of n we cannot find. So how will find n? We'll just substitute omega equal to omega s. So we know at omega equal to omega s, the gain of T of j omega will be T of j omega dB will be equal to, so at DC, okay, DC minus this a max, DC minus a max. So 20 log k minus what is a max, sorry, not a max, a minimum, right? This written as a minimum, so that is 60 dB. Okay, substitute the value of omega s, just do some the required computation. We'll find what is the value of n. Okay, so we'll see the solution. See, we know from the previous question epsilon equal to 0.997. We have computed this. The transfer function of Butterworth filter is this in general. We'll substitute at omega equal to omega is the gain. So gain is 20 log k minus 60 dB. So again we know 20 log of a by b is 20 log a minus 20 log b. So I have written it or splitted that, and this will cancel off. Okay, just few computation, we'll get 10 power 2n equal to this term. So what is the n? N value will be 3.00 something value. So we can take it as 3. So n equal to order is 3. Okay, so I guess it is pretty much straightforward, right? So you just need to substitute the given values here, some computation, we will find what is the value of epsilon and n. Okay, just simple mathematics there. So that's all about the today's question. I have solved 10 questions. So any doubts, you may please Please ask.
Sir, this
Yes.
this Butterworth prototype filter was discussed in detail in the module.
Was
Um,
discussed in detail. Okay.
means in module in week 6.
Hello. I think
Uh,
your voice is cutting. Yeah. In module 6, it has been discussed.
no, sir.
No.
In week 6, module 1.
Huh. I think your voice is breaking. Can you just type? I will just check. Okay. Are you Siddharth? Your question. Like you have.
Yes, sir.
Haha. So, sir, in which module the Butterworth filter was discussed? Actually, in this fifth week, in tutorial session, you would have seen the how Butterfield filter is designed, and I will just check. I will show you in a log. Okay, I'll show you. Just check the tutorial. I think tutorial 5 or 6. I don't remember correct. So it is week 5, right? In week 5, you can see in this tutorial. Okay, you just check tutorial 4, 5, and 6. So I guess in 5 or 6, it has been detailed how the Butterworth filter is designed, and how the same, similar to the same question that we have discussed. The same thing has been discussed in this tutorial. I think sir will also explain related to Butterworth, as well as Chebyshev filter in week 6. So you can go through these tutorial 5 or 6. Also, I think in module 3, filters also some part has been discussed. You just check that. Okay. Okay, Siddharth. Yeah. Any other questions?
Sir,
Huh.
sir, actually, I was unable to attend 4 week classes
Okay.
because of
Okay.
semester exam, and
Okay.
so and also the assignments were not submitted properly.
Okay.
Uh,
Okay.
so, um, how many total assignments will be given, sir?
I think you should check how sir has mentioned about the criteria. See, like criteria to get a certificate, right? So average assignment score is 25% of average of best 6 assignments. So 25 percentage average of 6 assignments. Okay, best 6. So if 8 assignments are there, the mark will be taken as 25% of 6 best assignments. Okay, and exam score 75% of the proctored examination. So final score will be average plus exam.
Okay, sir.
I think you should also check this eligibility for the certificate. Okay, what
Yes,
is the
sir.
value? Okay. If you have doubt, you can ask. So the session will be till 9 o'clock. So I'll wait here. If you have any doubt, you can ask, or if no means you can even leave. Don't worry. But if you have any doubt, you can post it in the message or you can ask. Okay, I'll be there till 9.
Sir,
Yeah, yeah, hello. Yeah.
sir, in NLOPS, that is the loop gain decrease the
Hello.
sir, the loop gains slope changes from -20 dB to 60 dB, -60 dB.
Okay, minus 20 to 60 dB, correct. Means
Um, so why, sir, in why g of s loop changes from I mean g of s slope changes from -20 to -40?
where in this one? So, say eighth question.
No, sir. In third question, sir.
Okay, okay, third question. Check. Third question, yeah. So,
Sir, you when you drew that diagram, no, sir.
ha ha ha,
Yeah. Um,
this one, right?
yes,
Okay,
sir.
so initially it starts from minus 20 at s equal to 5 or omega equal to 5, it will tend at minus 60. Correct.
This is for loop gain, no, sir.
Yeah, loop gain as well as here the loop gain and g of s is same, right? Because h of s equal to 1.
Yes, sir.
So both for g of j omega means for in this question g of j omega or loop gain g of s into h of s, for both this is same. Did I draw it as minus 40 previously?
No, sir. It was -60 only.
Okay, okay, then no problem. Okay, so that's it. So this is the proper way. So, okay, it's already 9. So let me conclude the session. So let us conclude this session. So we'll have the next tutorial session on next Tuesday, that is 14th.